We're good? Okay. Well, Martin, let's go. Thank you.
Cake is being cut up into little crumbs, and the key idea that we're going to see is that we can measure the size of a slice of cake in terms of these little discrete crumbs of which there are an integer number. So first let me tell you a bit about cake cutting. So if you suppose that we have two agents, Alice and Bob, and they want to divide a cake, here's a well-known way that they can do that fairly. So Alice cuts the cake in half, Bob chooses one slice, Alice takes the remaining slice, and then we believe that they will both be happy. So why do we believe that they will both be happy? So when Alice cuts the cake in half, she's not getting out a tape measure or scales and dividing it exactly into two measurably equal slices. She's making a decision about where to cut the cake. Oh, and by the way, this cake is represented by the interval from 0 to 1. She's making a choice about where to cut the cake, where she believes that the two halves will have equal value. So they may not be equal, and it may be visibly that they have different weight, but maybe she prefers what's on one side of the cake to the other, so she puts the line a bit to one side to express her preferences. When Bob chooses a slice, he's looking at the two slices and saying which one he thinks is bigger or more valuable to him, and he's going to pick honestly which one he prefers. So ultimately, Alice ought to be happy with either slice because according to her, they have the same value, and Bob got to choose what he preferred. And if the whole cake had a value of 1, then one of the two slices must have a value of at least a half. So ultimately, they should both be happy, and neither agent should envy what the other got. Okay, so I've talked about cutting cake, but in the literature on economics, mathematics, and so on, the cake could in fact be any kind of continuous resource that can be split between multiple agents. So it could be land, or it could be advertising space, or something like that. And when we have a cake cutting protocol, the input to the protocol is going to be a valuation function for each agent that says, for that agent, what's the value of a particular region of the cake. And the output is going to be a partition of the cake, this interval 0, 1, into a finite set of disjoint intervals that are allocated to each agent. So you can't give the same bit of cake to more than one agent, and you only get to make a finite number of cuts, so you can't have weird fractal slices. You only get a finite number of intervals to give to each one. We don't necessarily guarantee, or we don't necessarily require, that the whole cake ends up being allocated. So we might throw away a little bit if we can't agree what to do with it. There are lots of properties of these protocols that have been studied in the literature. The most relevant one today is envy-freeness, which is that no agent would prefer any other agent's allocation. And we're also interested today mainly in finite protocols that are guaranteed to terminate and bounded in the sense that you can say in advance that you're not going to need more than a certain number of cuts. Let's talk a little bit about these valuation functions. So they really are mathematical functions, not computable functions. So they might not be finitely representable, but what we can do is query each agent about the value of a particular slice and get back an answer. There are a load of standard assumptions we can make about the form of these valuations so that we can get meaningful protocols, but intuitively you can think of the valuation as specifying like a cake density function. So you can express a wide range of different preferences here. So you could express, going back to my earlier example of Alice measuring the cake, that she wants the heaviest possible slice in terms of grams, but you can't express that she has a limited appetite. So you can't say she wants 1/3 of the cake, but she has no further value of getting a half of the cake or 2/3 of the cake. You can also express that a particular part of the cake is more valuable than another part. So Bob can think, I love strawberries, I want the part of the cake with strawberries on. But you can't express that he'd rather have a whole strawberry as opposed to 2 half strawberries. Okay, so here is an example of a protocol written in my embedded DSL called Crumbs, which is embedded in C. And this is the cut and choose protocol that I described involving Alice and Bob earlier. So just to give you a quick run through this, we create some variables that are cake slices. We construct our whole cake as a slice. Then we get Alice, who's agent 1, to split the whole slice into 2 halves, left and right, that she believes are equal. We ask agent 2, Bob, is the left slice smaller than the right one? If so, he gets the right one and Alice gets the left. Otherwise, Alice gets the right one and Bob gets the left. And finally, we check the whole thing's envy-free. So you might wonder, how is this declarative? Because it's basically imperative C with this sort of API that gives you cake cutting operations. And I claim it's declarative because we're not actually going to execute this program. It's a way of expressing a set of constraints. And what we're going to do is pass this program to the model checker, CBMC, and using non-determinism in the model checker, we're going to express these constraints. It's going to collect them and translate them into SAT. And if the constraints are unsatisfiable, so the SAT instance is unsatisfiable, that means the protocol is envy-free. So the declarative aspect is more about how we're using C as a constraint programming language rather than in the expression of the protocol itself. Right, so just to give you a bit of an outline of the talk, I've introduced cake cutting. We'll see some previous work and results on cake cutting. I'll introduce the basic operations in the Crumbs DSL. A key idea in the verification is that we can do it using just bounded integer arithmetic. We'll then see a bit of the implementation and how we get CBMC to do what we want. And finally, we'll have some empirical results. Okay, so let's look at some previous work. There's a vast body of existing research on the topic of cake cutting. Here are a couple of the most significant results. So in the 1960s, Selfridge and Conway independently developed a protocol for 3 agents, which is quite well known. What's interesting about this, and most subsequent protocols, is that you may have a slice that's cut by one agent, which gets further subdivided by the other agents. So this means that an agent isn't going to end up with a contiguous piece of cake. You might end up with one big slice and like 2 or 3 small slices. So this idea was developed for many years, and people wondered if there was a protocol that worked for any number of agents. And Aziz and Mackenzie came up with one in 2016, which has the property that the number of slices is bounded by a finite number for a particular of agents, but the bound is an exponential tower in the number of agents. So we can see that these protocols can be very complex, and so verification might be needed. Which brings us on to a previous DSL for cake cutting, presented at PLDI last year by Bertram, Levinson, and Su, called Slice. And this uses 2 low-level primitives from what's called the Robertson-Webb model. So this is one of the standard models of cake cutting. So these are the mark and eval primitives. So here we can see the cut and choose protocol in their DSL. Mark is saying agent 1 picks a slice starting at 0, which is the left end of the cake, that has a value to agent 1 of a half. And here we're asking agent 2, what's the value of the right side and the left side, and then we compare them. So there's one problem with this. The verification procedure for this DSL works by doing an encoding in the SMT theory of quantified real arithmetic, which is solved with Z3. And unfortunately, that decision procedure and the SMT solver, the complexity is bad, and the solvers are usually quite slow in practice. So while this DSL is quite fast for envy-free protocols, it's slow for the envy-inducing protocols where there's something wrong. Can we fix it? Yes, we can. So in the DSL Crumbs, what we do instead is we adopt a different set of slightly higher level primitives. So we can split a cake into several slices that an agent believes are of equal size. We can take a reference slice and a larger slice and trim a bit off the larger slice so that it's the same size as the reference slice. And we can ask an agent to compare two slices. And by doing this, we can come up with a verification procedure that just uses integer arithmetic, and we get a pure encoding into SAT, which we can solve with KISSAT. And this turns out to be very fast for envy-inducing protocols, or at least the ones that we tried. Okay, so let's take a bit of a look at this DSL. So what are the data types and operations that are provided within C for expressing our cake-cutting protocols? In terms of data types, we've only got two. We've got integer IDs to express the names of agents, essentially. And we've also got a slice data type that represents an interval of the cake. There are a number of operations available, but here are some of the most important. So cake gives us back a single slice that comprises the whole cake. Halve, we ask agent A to take a big slice, which might be the whole cake, and split it into two equal slices on the left and the right. So these are equal from the perspective of the agent. They might not be equal from the perspective of the other agents. And analogously, there are versions for 3 or 4 equal slices and so on. We can ask an agent to trim a slice, in which case he takes a reference slice and a big slice and trims a bit off the end so that there's a big bit left that's equal to the reference slice. And it's an error to do that if the agent believes that the whole slice is smaller than the reference. Okay, and then we do all this cutting. At some point in the process, we're probably going to ask the agents to compare the slices. So we can ask an agent, do you believe that the left slice is smaller than the right slice? And we allocate the slices to the agents, and then we check that the allocation really is envy-free at some point. So those are some of the operations that are available. There are more described in the paper. Right, so the key idea in terms of getting the verification to work is that we have to use bounded integers to make things discrete. So I said earlier, real arithmetic is slow to reason about. We want to use integer arithmetic. And there are a couple of decisions that we've made in the design that make this possible. So in particular, the protocols can't directly manipulate the values of slices or the positions of the slices on the cake. So they can't do integer or real arithmetic with positions or weights of slices. What they can do is cut them so they're equal value and compare the values of sets of slices. So why does this allow us to use integers only? So here's an intuition behind why it works. And you can read the full argument in the paper. So if you've only got a protocol with a finite bounded number of cuts, then although your weights of your slices might be real, you don't have any weird behavior with irrational numbers and infinite sums and so on. So you can use rational numbers to approximate them with arbitrary precision. So you end up with a situation where any relationship that's realizable with real numbers in terms of inequalities over sums of sets can also be realized with rational numbers. If you multiply out the denominators on the rational numbers, you end up with integers. Okay. But do we know if the integers are bounded? Well, with only finitely many different slices, there are only finitely many different possible conjunctions of orderings of sums of sets of slices. And each of these is realizable in integers, so necessarily there must be a maximum integer that's needed. So that's an informal argument for the existence of a bound on the integers you need. But in order to turn this into a verification procedure, we need to bound it. Can we bound it? Yes, we can. And the actual bound turns out to be O4 to the n. And yeah, you can find the computation in the paper. Okay, so how do we go and turn this into a verification procedure using CBMC? The fundamental idea is that we need to write definitions for these operations in Crumbs so that if the program violates an assertion, then the program is going to be envy-inducing. I'm going to pass that to CBMC. It'll translate the problem of finding the assertion violation into SAT, and then we'll solve that with KISSAT. So we already talked about integer arithmetic, which was one important observation. The other important observation in terms of efficiency is the fact that we can focus on an agent. So what do I mean by that? We haven't decided yet how we're going to model a slice of cake. So naively, you could think of it as being an interval of 0 to 1, or if you're using integers, you can think of it as being an integer up to some bound. And you could think of modeling the value of that slice for each agent. However, if you're interested in proving that a protocol is envy-free for all agents, it's sufficient to prove for each agent in turn that it's envy-free for that agent. And this is advantageous because instead of having one big verification problem, you can have a small verification problem for each agent. So that may give you an efficiency boost. And the rationale for this is that if we're trying to determine whether Alice is going to be envious, she doesn't know or care how much Bob values each slice. She only cares how much a slice of cake is worth to her. So we're going to focus on one agent at a time, and we're going to model a slice as its value to the focused agent. And the unit of value is going to be what we call crumbs, which are these integers within a particular range. Okay, so now we're going to see the implementation of some of the operations that we saw earlier. So a slice of cake is just a C struct that lets us specify the position of the left and right ends in this unit of crumbs. When we create the whole cake, we're going to use verifier non-determinism to pick how many crumbs are in the whole cake with the restriction that it must be less than this bound that we've computed. When we go and cut the cake, again, we use verifier non-determinism to pick a point in the middle of a slice, with the restriction that it must be between the left and right ends of the slice that's being cut up. If we want to cut the slice in half according to a particular agent, if the agent isn't focused, we can just cut anywhere. But if the agent is focused, we have to make sure that that agent believes that the left and right halves that we cut are the same size. So we're going to use this cProveOrAssume function of the CBMC verifier to restrict our attention only to paths of execution where that is true. And similarly, if we want to trim down a reference slice, trim down a large slice to match a smaller reference slice, again, we cut the larger slice into two small bits, and we're going to require that the focused agent, if she's doing the cutting, thinks that the value of the trimmed slice is equal to the value of the reference slice. And you may recall I mentioned that it is an error to try to ask an agent to cut a slice down to a particular size if it's smaller than the reference. So we need to add in an assertion there so we can check that too. Okay, so finally, after that, we need to think about adding up all the values of the slices. So the value of a slice is just the distance in crumbs between the right end and the left end. When we want to ask an agent, is one slice smaller than the other? If it's the focused agent, we look at what the agent thinks the value of the slices are. If it's not, we make it a non-deterministic choice. Okay, and then when we allocate the slices to the agents, we store a running total, we add them up, and then right at the end of our program, where we are checking that the agent doesn't feel envious, we do that just by asserting that all the other agents have a smaller or equal total to the focused agent. Okay, so that's how we translate all of those operations into grungy C with non-determinism and assumptions to restrict ourselves to only considering certain paths of execution. Okay, so what results do we get from this? So in the Slice paper, they looked at a number of protocols with up to 3 agents, and this is the original times for Slice. So I reran them on my own computer just so that the times are comparable. You'll see that the Slice DSL doesn't take very long to compile, and then Z3, in most of the examples, it was really fast, but this one at bottom, it took less than a minute, so it was still quite fast. With Crumbs, what happens? Well, we have 3 separate subproblems, potentially, for the protocols with up to 3 agents. So we've got separate measures for those there. And we can see that for the simpler protocols, it's still pretty fast. And then for this complicated one, we are slower than Slice, but still acceptably fast. And in case you were wondering, because we've got time spent by CBMC and time spent by KISSAT, CBMC was like less than 0.01 of a second in all of these cases. So this is almost entirely SAT solver time that we're seeing here. Yeah, so it seems good enough for that, although we'd really need to look at some harder protocols to stretch either system. But what about envy-inducing protocols? Because that was part of my main motivation for looking at this alternative formalism and looking at the integer arithmetic. Well, in order to benchmark that, I introduced some errors into a variety of these cake-cutting protocols. And with Slice, even the very simplest protocol where agent 1 cuts and chooses, it couldn't show that it was envy-inducing because the SMT solver didn't find the solution. So even after like half an hour, didn't show any obvious progress. However, with Crumbs, all of these solve in less than a second. So it's really fast. So why is showing a protocol is envy-inducing comparatively so fast? Well, when you want to show a protocol is envy-free, you have to solve an instance and show it's unsat. When you show a protocol is envy-inducing, you have to solve it and show it sat. And as a rule of thumb, showing unsat is slow, and showing sat is fast. So just to summarize and wrap up, in the Crumbs DSL, we used integer arithmetic and encoding into sat, as contrasted with Slice that used real arithmetic and an encoding into SMT. It was fast for bug finding in protocols, and the key insights that led us do this were focusing on an individual agent to split up the verification problem and calculating this explicit integer bound so we could use integer arithmetic rather than real arithmetic. In terms of future work, to test the limits of this, you'd really have to look at some harder protocols. There are a few statically verifiable safety properties that could be enforced. I've done a bit of work on those. I've chosen encoding into SAT just because I've been doing a lot of work with SAT and CBMC, and that's what I like to work with. But while doing this, I did wonder whether a good translation into a mixed integer programming solver might end up being faster. And the final question, of course, is whether there's going to be any cake at lunch. Thank you.
Questions? Looking online. None? Nobody? Okay. So one thing I noticed is that you have these halve primitive.
Yep.
And you said there was something for 3 or 4 parts or something. Why does it matter that it is not a generic function, so it's cut in n parts with n a parameter?
It doesn't matter. It was just easier to write the C that way. Yeah. So I probably could have turned it into a loop, but yeah. So the sort of C syntactic reason why it would be awkward to do that is if you notice. the operations that mutate the cake, they don't return a value. You pass in a slice object because it may be returning multiple slice objects, and that's not nice to do in C. So maybe you could have a generic version that has cut into n slices using variadic macros, but it wouldn't be nice to write. So yeah, that was the protocols I looked at only had cutting into 2 or 3 slices. So I thought, let's just do that for the moment.
Nobody thought of any question yet? Okay. One other thing I noticed. CBMC, you say, is a bounding model checker.
Yeah.
Sorry, I'm thinking as I'm asking the question.
Mm-hmm.
So usually when you have a bounding model checker, you get counterexamples, but when you don't get counterexamples, you don't have a proof.
You'll get a counterexample if it is an envy-inducing protocol.
Right.
Yes.
But if it says unsat,
yeah,
then you might expect, well, that just means if there is an envy-inducing situation, it's too complex for me to compute.
So CBMC, it won't introduce that kind of unsoundness unless you ask it to. If you have loops in your program, for example, it'll use static analysis to compute an upper bound on the loop and unroll it that many times, so you get completeness. Other bounded model checkers might by default have a limit on how many times they'll unroll it, and CBMC, you can tell it stop after 100 unrollings or something. So if your bounded model checker was incomplete, then it might not pick up the fact that the protocol could be envy-inducing. But CBMC's behavior is to be complete by default.
Right, and is that related to the bound on the integer that you compute as based on the number of participants?
Partly, yeah. So if you had arbitrarily large integers, then you wouldn't be able to do this. But then you wouldn't be able to express it using C integers because they're inherently bit width integers. So you'd be using some sort of big integer library, and then you'd introduce incompleteness through the big integer library. So the fact that you have this bound means that you have to pick an integer type, and there's something behind the scenes that chooses the best match. So you're only ending up with, for example, 16-bit integers, and it bit blasts its way through all the different possibilities.
Okay, one last sense from the audience or for the internet? No? Okay, then I guess lunch.
Cake time.
Cake time, yeah. Let's go.